Hello class, let's continue on with 4.1 and we finished off with this part, right? Where the sequence converges with e power 4 as the limit. So the next part here would be continuous functions. Defined on convergent sequences. Convergent sequences. Okay. Consider a sequence AN, and suppose there exists a real number L such that the sequence capital L, apologize, I just wrote that, such that sequence AN converges to L. Suppose F is a continuous function All right. I had to remain silent so that I could finish writing properly. Okay, so let's read this. Consider a sequence AN, and suppose there exists a real number capital L, such that the sequence converges to L. Suppose F is a continuous function at L, then there exists an integer capital N, such that F is defined at all values AN for n greater than or equal to that particular integer n. And the sequence f of AN converges to f of L. So in other words, if AN converges to L, then f of AN converges to f of L. That is the gist of this. Determine whether the sequence cosine 3 over n squared converges and find its limit. So I'd like you to consider cosine 3 over n squared as f of AN, where AN is your 3 over n squared, right? So the function is the cosine function. f is your cosine function, f of that an, which is 3 over n squared. Therefore, you'd want to see what 3 over n squared, how it behaves, okay, as n approaches infinity. So this actually approaches 0 as n approaches infinity, because your n is in the denominator. You can see that. Now cosine, for our the previous definition, continuous functions defined on convergent sequences. Now because your 3 over n squared an is a convergent sequence, if cosine of that 3 over n squared, the cosine function, if it is continuous, then we could apply this rule, right? So cosine is a continuous function. Therefore, it implies that f of an, which is cosine of 3 over n squared, right? I mean, as a sequence, so let's put the curly brackets, which is cosine of 0, right, as n approaches infinity. So this whole thing approaches 1 as n approaches infinity. You see the combination? Because we just saw that 3 over n squared approaches 0 as n approaches infinity. So cosine 0 approaches 1 as n approaches infinity. All right, squeeze theorem for sequences. Let's write the definition and then I will go over it. Let me also draw the graph and then I will start talking. Okay, I'm going to make this a dashed line. almost there. All right, now I'm ready to explain. Okay, let's read this. Squeeze theorem for sequences. Consider sequences an, bn, and cn. Suppose there exists an integer capital N such that an is less than or equal to bn is less than or equal to cn. Okay? So they are arranged in that order. And this symbol means for all n greater than or equal to capital N. If there exists a real number L such that the limit of an as well as the limit of cn, they both point to that L, right? As n approaches infinity. So if you look at the graph, we're saying, well, A must be bigger than B, B must be bigger than C, right? A, B, C is arranged this way. And we're saying if limit of an as n approaches infinity, and if limit of cn, the blue, the red and the blue, if they both approached L, you see here the capital L, the purple L, then we're saying the Bn, the sequence Bn, that's squeezed in between an and cn, will also have the same limit. It will also approach the same limit. Yeah. So that's the whole idea of the squeeze theorem here. So let's see where we can apply it. Use squeeze theorem to find the limit of each of the following sequences. A, cosine n over n squared. Well, to find the limit of this particular sequence will give us indefinite situation, or it could give us, indeterminate situation, or it can be undefined. We can have all those conditions, right? So try finding the limit for cosine n over n squared directly, right? As n becomes really, really, really large, cosine infinity over infinity squared, right? So that's the reason why we want to go with the squeeze theorem, but also because they kind of asked us to do that. So I'll start with this. Now cosine can take values, cosine of an angle, can take values only between -1 and 1, right? So cosine n should be a value between -1 and 1 for all integers n, because n is an integer, right, in the sequence. All right, next we go for, when we do the setup, what we see is we have cosine n. You want to do cosine n over n squared, but we're just beginning with familiar stuff. We're familiar with the fact that cosine n is a value, provides values between -1 and 1. And therefore, that opening helps us to build an inequality like that. And then what we're going to do is divide throughout by n squared. We do this so that we have a match with the given sequence. Also, it lines up nicely with the 1 and the -1. Okay? Because after this, we are going to apply the limit. So we say take limit n approaches infinity on both on all parts. Okay? So what happens is now with these n's, we can see that this approaches 0, right? And the limit for this also approaches 0. By squeeze theorem, it implies that the one that's squeezed in between, that is limit cosine n over n squared, will also approach 0. In other words, it will, because it's a limit, it will be equal to 0. B, negative half power n as your sequence. Now notice negative half power n, no matter what your n is, it's a value that's going to fluctuate between negative and the positive depending on the evenness or the oddness of n, right? So we know that it is going to be between the negative 1 over 2n and 1 over 2n, 2 power n. So negative 1 over 2 power n and 1 over 2 power n will be the extreme values, the n's, between which these fluctuating values will lie, right? So that is, again, by understanding the fluctuation of the negative sign. How far will it go? It goes as far as the sequence itself, but then it goes as far in the positive and in the negative. So that is the end limit or bounds for this. Now apply limit. Limit. And then explore what happens. The limit here approaches 0. I should say equals 0. This implies the limit of negative 1 over 2 power n that's squeezed in between these two limits will also approach 0. And we have bounded sequences. I have a few definitions here, so let's just quickly write the definition, then I'll go for the explanation. All right, so a bounded sequence, what does it mean? A sequence AN is bounded above if there exists a real number, capital M, such that AN is less than or equal to M for all positive integers n. That makes sense. If it's bounded above, then an, all an values should be under m, right? Because it's bounded above. And if an is bounded below, the sequence is bounded below, then all your ans are above that m. Right? Your m is the lowest value because that's below. It's bounded below. It's bounded above, m becomes the maximum value. Okay? So all your ans are below m, all your ans are above. And if we say an is a bounded sequence, it implies that it's bounded above and below. And when we say a sequence is not bounded, we simply call it an unbounded sequence. Then let's look at the relation between convergent sequences and if they are bounded or not. So convergent sequences are bounded. Okay? If a sequence an converges, then it is bounded. If it's convergent, it automatically implies that it's bounded. Right? That's what this theorem says. However, the reverse is not true. If the sequence is bounded, it does not mean it's convergent. Sounds a little off. Let me write this now. Bounded does not imply, so I slash it off, does not imply that it's a convergent series. So is there an example? Yes. Example would be a sequence that alternates in their sign, right? So this one is bounded. Why? Because it goes as far as -1 in the bottom, and it goes as far as +1 on the top, right? Those are the limits. It does not exceed that on the top or on the bottom. But you know that because they are bouncing around between -1 and 1, it is not convergent. So this is bounded. This sequence is bounded, but divergent. That's why we say bounded does not imply convergent. However, convergence implies boundedness. So here's the definition. So let's write this down. All right. A sequence AN is increasing for all n greater than or equal to n naught if an is less than or equal to an plus 1. Okay. In other words, you can think of this increasing, right? Increasing in your mind, you know how it's rising. So what we're trying to show here is, as you go from one term to another in your sequence, as you move on, the values of your sequence will keep increasing. That's what it means, right? An plus 1. N plus 1 is a term after an. So say n is 3. An would be A3. So an plus 1 would be A4. So we're saying A4 will be a number that's bigger than A3, right? Because A3 is less than or equal to A4. If that's the case with every such term, then you know that your sequence is increasing. If your sequence is decreasing, then it's the other way around, right? So A3 will be greater than or equal to A4. So, you know, as we keep moving through the terms, you notice that your values are getting smaller. So you know that your sequence is decreasing. So any sequence that increases or decreases for all such n's greater than or equal to n naught, we call that sequence as a monotone sequence. You've heard this before in Calculus 1. Increasing and decreasing information on a function, on a graph, tells us if it's a monotonic function or not. Here we're talking about the same idea, but in a sequence, the monotone sequence. We have a monotone convergence theorem. An is a bounded sequence. All right. Monotone convergence theorem. If an is a bounded sequence and there exists a positive integer n naught such that an is monotone for all n greater than or equal to n naught, then an converges. Well, monotone convergence theorem is so important because we previously established, let me take you back here, that convergence implies boundedness, but boundedness does not imply convergence. We saw that because -1 power n was bounded, but it diverged. It diverged because it was not monotonic, right? So that is what this theorem addresses. It says, if you have a sequence that's bounded and monotonic, then that sequence will converge. Just bounded does not imply convergence, but bounded plus monotone implies convergence. Here's an example. Use monotone convergence theorem to show the sequence converges and find its limit. We need to show that this sequence converges. Okay, that would mean that if we can show that it's bounded and monotonic, then we can show that it's convergent, because that's what the monotone convergence theorem wants us to. to show. Expand the sequence. Four, 16 over 2. After that, it becomes really big. So I'm just going to write this. Now remember, we are trying to see its monotonic behavior. So try to expand into as many terms as you want to be convinced of the pattern. So I want you to pull out your calculator and see how these values develop. So that's an 8. That is 10.6 repeating. That's also 10.6 repeating. And use the factorial button, right? You know the factorial? This is mostly used in statistics. N factorial is, the exclamation mark is read as factorial, right? This is how it expands. You multiply them out. And so if it is 5 factorial, it's 5 times 5 minus 1, right? 4 times 3 times 2 times 1. And you multiply them out, and that gives you the answer. 20 times 6, 120. Okay, 5 factorial is 120. So use your calculator option to find the factorial. Okay? It will mostly be in a function key that is to do with statistics. The next one was 5.68. I put that here as 4.6. Then you have the values decreasing. At first it's increasing, okay, right? So 4, 8, 10, 10, and then it begins to decrease, right? So remember, again, the definition says it doesn't have to decrease everywhere. Every term should show that. It says it should begin to steady out after a certain n naught, right? For all n greater than or equal to that particular n naught. So in the beginning, it may go up and down, fluctuate, but then after a point, you should see it stabilize, and you should say with certainty that it stabilizes after this particular n naught. So that's what we're observing now. So we see that it's increasing in the beginning, but then it begins to decrease. So I'm making a note here. At first the terms increase, but after the third term, you see that the terms decrease. So if I were to write a general version of this, right? Remember, why I'm doing this is a way to understand how I can establish, what I'm trying to do here is to establish that okay, I'll take you back to the theorem. It's actually easier. So if it is decreasing, right, I'm trying to establish this, okay? I'm trying to show that an is greater than or equal to an plus 1. In other words, an plus 1 is less than or equal to an. And for that, I have to show it happening after the third term, when n is greater than or equal to 3. Therefore, that's the reason why I begin to write in the general form. I have to start with an plus 1 because only then can I rewrite that in terms of an, right? If you start with an, you can't write it for the next term. But if you write it for the next term, then you can work backwards and find what it is for the previous term. In this case, the next term was n plus 1, so you're able to break this down as n. So I could split this up as 4 power n times 4. And by factorial property, this will be n plus 1 factorial times n plus 1 minus 1 times n plus 1 minus 1 minus 1, and so on, right? So this is n plus 1 times n plus 1 minus 1 will be n factorial. If you want, we could I can show it to you. One more step. And the ones cancel off. That's how you're left with the n factorial. There is 4 power n. And I want to bring the n factorial down to this and split up the product so that the 4 and the n plus 1 are together. Again, remember this is to rewrite this in terms of an. And so we know that an, if you go to the problem, an was 4 power n over n factorial. So when I get that form, I want to utilize it. So an plus 1 is an times 4 over n plus 1. So what do we know about an plus 1? An plus 1 is an multiplied by 4 over n plus 1, right? Before that, let me just write that this is recursive formula, because you wrote one term in terms of another term, rather previous term. This establishes that an is a bigger term. Think about this. Although you're multiplying for an plus 1, you have an and you're multiplying it to another number, that number should be a number that's big to increase the value. If you look at n, each time you have an n that's added, so that is going to actually reduce how it gets multiplied, right? Reduce the value of it. Therefore, an is bigger than an plus 1. An, the term before an plus 1, is bigger, and that means it's decreasing. We saw this happening in these numbers here, right? And it happened right after 3. But in order to, we saw that it was decreasing, but we have to prove that it's decreasing. And we were able to do that by putting it in the recursive form, and then we were able to show that the sequence was decreasing. So I'll say since an plus 1 gave this relation, is less than or equal to an, the sequence is decreasing for all n greater than or equal to 3. Oh yes, now by the way, let's understand that this n greater than or equal to 3 is crucial, right? If n is 3, let's test it at 3. If n is 3, this will become 4 over 3 plus 1, so 4 over 4. So an plus 1 is the same as an, that's what we got, right? If n is now the next number, 4, the 4 over 4 plus 1, 4 over 5 is a proper fraction, and so it's going to be a value less than 1. So you're multiplying an with a value less than 1. That's the reason why an plus 1 will be a number smaller than an. But this won't be true for n equals 2 or n equals 1, because then you'll have an improper fraction, thus making an plus 1 bigger. That is what, again, we observed in the beginning. Numbers were increasing when n was 1 and n was 2. When n was 3 and n equals 3 and n equals 4 were the same, and then it began to decrease. So that is where the change happens, and that is where you will even begin to see that the sequence is decreasing in the in the general form. Okay? All right. This sequence, you can see that this sequence, when it begins at n equals 1, it starts at 4, right? Because it starts at 4, you can kind of see that it's not going to go below 4, right? And to keep, to give more room, to be more conservative, you can kind of say that the bound for this one below, for this sequence, the lower bound can be set at 0. Right? It's bounded below by 0, you can say, because all of these are going to be positive. Let me write that down here. So we found the sequence to be decreasing, so that's monotone. And if I can establish boundedness, then I could use the monotone with the boundedness to imply convergence. Okay, for all n, this implies by monotone convergence theorem. Bounded plus decreasing implies that the sequence converges. If it converges, we know that the limit must exist and produce a finite number. Let's see what happens with a n plus 1. If it's n plus 1, we start at 2. This means that if you took the sequence an plus 1, that sequence omits the first term, right, from an. So you can write an plus 1 as 4 over n plus 1 an. So this implies limit an plus 1 as n approaches infinity. Separate the 4 over n plus 1 from the an, because we know that limit an approaches L. That's an assurance that convergence gives us. We know that it's convergent if, because of the boundedness and the decreasing. Right? So it has to converge to some L. See what happens here. When n approaches infinity, this becomes a 0. 0 times this becomes an L, which is 0. They wanted us to find the limit, right, of an plus 1. And so we got that. We were able to establish sequence converges. They wanted us to do that using monotone convergence theorem, and we were able to find the limit. I want to wind up with this one application. You've heard of Fibonacci series? We're talking about Fibonacci numbers. The use of Fibonacci numbers is in architecture and construction. It leads to the golden ratio. And so I just wanted to give you a quick glimpse of that to see how this matters. Fibonacci numbers are defined recursively, meaning one term written instead of the previous term. Okay. Where f naught is considered 0, f1 is 1, and fn is fn minus 1 plus fn minus 2. Okay. So if you took the ratio of fn plus 1 over fn, if you did the computation, right, you get what is called as a golden ratio, 1 plus square root of 5 over 2. A golden ratio is denoted by the symbol phi, and this one is called the golden ratio. Well, it's used in architecture, particularly in the Parthian Greek temple. There's a Parthian Greek temple. And in nature, you can see it in sunflower seeds, the arrangement of the sunflower seeds. You can see it in snails, and so on. So I'll just give you a quick look of how it is. So if you just divided this rectangle into a square, which is a square, right? 21 and 21. Divide this into a rectangle, that produces a square of 8 here. Divide this into 5. That's kind of the ratio for each time you divide this. The ratio is maintained, the phi is maintained. Okay? All right, class, I will see you in 4.2 in the next video.